Chapter 11, Lecture 2, Actual Refrigeration Cycles. An actual vapor compression cycle differs significantly from an ideal one in several ways. Mostly this is a result of various components having irreversibilities. These irreversibilities are caused mainly due to fluid friction and heat transfer loss to or from the surroundings. Therefore, as a result, the coefficient of performance decreases. So this slide shows the difference between the ideal cycle and the real cycle. Namely, you have a non-isentropic compression, and you have a subcooled liquid at the condenser exit. To illustrate the differences between the actual refrigeration cycle and an ideal cycle, let's take a look at example 11-2. Here we have refrigerant entering the compressor of a refrigerator as a superheated vapor at 0.14 million pascals and minus 10 degrees C at a rate of 0.05 kilograms per second, and it leaves at 0.8 million pascals and 50 degrees C. This refrigerant is cooled in the condenser to 26 degrees C and 0.72 million pascals, and is throttled to 0.15 million pascals. If we disregard heat transfer and pressure drops in the connecting lines between the components, we want to calculate the rate of heat removal from the refrigerated space and the power input to the compressor, the isentropic efficiency of the compressor, and the coefficient of performance of the refrigerator. So given our data, we can look in our tables. We can find the enthalpy value, H1 and H2. We can find the enthalpy at H3. And H3 is going to equal H4. This is a throttling valve. So all these values can be looked up in the tables. The rate of heat removal from the refrigerated space and the power input to compressor is determined basically from their definitions. QL dot is M dot times H1 minus H4. We can find that value. M dot is given. So we can calculate it to be 7.93 kilowatts. The work in is M dot times H2 minus H1, and again, we can calculate that value, 2.02 kilowatts. These come right from the tables. The isentropic efficiency is determined from the formula, H2S minus H1 divided by H2 minus H1. Here, the enthalpy state at 2S, the pressure is 0.8 million pascals, and S at 2S is equal to S1, so that's 0.9724 kilojoules kilogram Kelvin. That turns out to be 284.20, so we can look that value up in the table again. Thus, the isentropic efficiency is calculated to be 93.88%. Given that value, those values, we can also calculate the coefficient of performance. It's QL dot over W dot N, which is 7.93 kilowatts divided by 2.02 kilowatts, or 3.93. So this sort of shows the differences. And again, you have to go into the tables to look these values up, but we're pretty proficient now at going into the tables and pulling these values out. So one thing that always brings up is, how do you select the right refrigerant for a refrigerator? Well, several refrigerants may be used, such as CFCs, ammonia, hydrocarbons, carbon dioxide, even air, even water can be used in certain applications. Over 90% of the market, of course, uses R11, R12, R22, R134A, and R502. Those are the standard. The industrial and heavy commercial sectors, of course, uses ammonia, but it's pretty toxic. So, for home use, it's not very good. R11 is used in large capacity water chillers, serving air conditioning systems in buildings. R134A essentially replaced R12, R12 was found to be damaging the ozone layer back in the 70s and 80s. So they pretty much got rid of R12 and they use R134A. These are used in domestic refrigerators and freezers, as well as automotive air conditioners. R22 is used in window air conditioners, heat pumps, air conditioners in commercial buildings, and these in large industrial refrigeration systems. It's pretty much catching on a lot because it's not as toxic as ammonia. R502 is sort of a blend between R115 and R22. This is used in commercial refrigeration systems such as those in supermarkets. So one problem with some of the refrigerants is that the CFCs cause problems with the atmosphere. So CFCs such as R11, 12, and 15 do the most damage. So that's why we've actually developed these other refrigerants, like R134A primarily to combat this problem. So two important parameters that need to be considered in the selection of a refrigerant are basically the temperatures of the two media. I mean, what are you trying to cool, and what's the environment you're in? That's pretty much what determines which one of these you're going to use. So heat pump systems reversible heat pump systems are sort of popular down south. If you get south of, well, I would say probably south of Memphis and south of Little Rock, you tend to see these heat pump systems pop up a lot more. One advantage of them, of course, is they're reversible. They can cool your house in the summer and heat your house, in the wintertime, basically by running in reverse mode. There's two modes. There's a heating mode, and there's a cooling mode. And basically, it uses a reversible valve to basically reverse the flow of you can see the flow here in the cooling mode, and the flow here in the heating mode. So basically, the big difference is that in the heating mode, the outdoor coil is an evaporator, while the indoor coil is a condenser. But in the cooling mode, it's a similar cycle, but the outdoor coil is now the condenser, and the indoor coil is the evaporator. So it's sort of, you can see the difference in flows. One advantage of these things is there's not a whole lot of parts to these things. They're pretty simple actually to work on and design. The problem with them, of course, is that it uses the Earth's the atmosphere as the energy source for the heating and cooling, and if you get down much below freezing, they're not going to work very well. So if it gets down to 20 degrees outside, your heat pump's going to pretty much run all the time, and your house is still going to be kind of cool. So that's a lot of times what they put these electrical coils, on the outdoor unit, here, and they're basically use I squared R kind of losses, and a lot of heavy current through a resistor, heat it up, and then blow the fan across it. And of course, that uses a tremendous amount of energy to do that. So when it gets really cold, your electric bill is going to be tremendously high. That's also why heat pumps aren't very popular, up above, north of Arkansas, up in the Missouri, and certainly in the Northeast. These heat pumps just wouldn't be able to keep your house warm in the wintertime. So again, as this points out, the most common energy source for heat pumps is the atmospheric air. You can use, water sources like groundwater, what's called geothermal heat pumps. They're sort of catching on a little bit now, but they're more costly for the initial install. And as this points out here again, that the efficiency of the heat pump falls significantly at low temperatures, and so you have to have a supplementary heating source, such as these electrical resistance heaters or gas furnace. That's the way to go.